So I welcome you all to the 4-week executive development program on data analysis and research, which is about to sharpening these skills through MS Excel and R software. And today is the 15th day for R software and inferential statistics. And I welcome you all who are participating in this program. And today we have with us the Dr. Arnav Kumar. So speaking about Dr. Arnav Kumar, he is currently an assistant professor in the Department of Management Studies at Ramanujan College, University of Delhi. He has done his post-graduation with distinction and doctorate from Department of Commerce, Delhi School of Economics, University of Delhi. He is having a rich experience of more than 8 years of teaching postgraduate and undergraduate courses in management and commerce. And he specializes in statistics, analytics, research methods, and has research interest in finance and investments. He is also the managing editor of Ramanujan International Journal of Business and Research, RIGBR, which is listed in UGC Care Group 1. A vivid researcher, he has published 16 research papers in national and international journals of repute, including ABDC listed categories of journals, and has presented research papers in about a dozen national and international conferences and seminars. He has received 9 Best Research Papers, Project and Presentation Awards at different national international conferences. He has provided consultancy in major UGC, ICSR, and DU innovation projects. He has undertaken 36 sessions as a resource person, invited speakers, including in MHRD-sponsored national level FDPs, workshops, and 1-month faculty induction orientation programs at institutions such as Sri Ram College of Commerce, Hansraj College, in University of Delhi, and also in various B schools of this nation. He has conceptualized and conducted a specialized diploma and certificate courses on contemporary topics such as financial modeling, business analytics, and research and data analysis. So this is a small bio of Dr. Arnav Kumar. So on behalf of the whole organizing team of Accounting Finance Lab and Department of Commerce of Ramanujan College, I welcome you, sir, over to the session. I welcome all the participants to the 15th day of this special lecture of Dr. Arnav Kumar for this inferential statistics, which is relating to the software. And hopefully, Dr. Arnav Kumar's expertise and specialization will benefit you in many manners. And hopefully you all are gaining since the program started. So I request Dr. Arnav Kumar to please come over and take over the charge of the session. Dr. Arnav, sir.
Thank you so much, Saurav sir, for the introduction. Really, it has been a great journey because of colleagues like you and learners like the participants. So thank you. And thank you to Kavaljit sir, Suchi ma'am, Anshika ma'am, Saurav sir, and other team members who gave me the opportunity of taking these sessions in the program hosted by AFL, Department of Commerce, Ramanujan College, in association with the Teaching Learning Center. Okay, so participants, we will now be beginning with the session. So I will be sharing my PPT. So first, I will be taking you through the basic concepts and background of the topics that we have to cover. So over the 3-4 days that we have, we will be covering inferential statistics, and then parametric tests, non-parametric tests, and correlation regression using the R software. And I believe in the last couple of days, you already have had an acquaintance with R software. So I would request all the participants that they please revise, and whatever you have been instructed, please practice and download, so that in my sessions, you will be able to implement it, because the analysis will be possible only when you know the basics of R. So revise it and be ready, because I will be directly taking you ahead with the hands-on sessions on various data sets. So I will be sharing with the organizing team some data sets also, data sets as well as the learning resources in form of this PPT. So it will be easier for you to revise and understand the key concepts. Okay, so we will begin by talking about the inferential statistics, and once again, also a little thing that we have a long session today because of some urgent engagement. So I hope you bear with us throughout. And though we will have a separate doubt session, but if you have something, you can press write in the chat. If possible, we will take it up. Otherwise, we already, as per the schedule, we already have a separate doubt session for the sessions that we are having today. Okay, so as you all know, that statistics or data analysis has broadly two parts, the descriptive part and inferential part. So let me conceptually explain to you why and how there is a separate inferential statistics and a descriptive statistics. So in descriptive statistics, we are limited to the study and analysis of the sample at our hand. See, in the entire context of research and data analysis, what we are trying to achieve fundamentally is that we are trying to use the sample data to predict about a larger population. I will tell you some examples that will help in elaboration. For example, during the last 2 years of COVID pandemic, after every major wave in our country, there was a zero survey that was conducted. Zero survey was conducted to find out the presence of antibodies. So if you have basic idea was that if you had been exposed to COVID knowingly, unknowingly, whether you tested or not tested, you would be having antibodies, COVID antibodies in your blood. So if there is antibodies that is found in the zero survey, that means that percentage of population was exposed indeed to the COVID coronavirus. So now this survey ought to be ideally in an ideal situation, every Indian should have been tested, or in other parts of the world also every person should have been tested. But you can just imagine the magnitude and the time and the cost and effort that will be required if we want to test each of the close to 140 billion people, 140 crores people, 1.4 billion people. So that scale of exercise is not possible, that too at such a small frequency of that is like an year. So the alternative was that we carry out a smaller sample survey. So around 20, 30, 40,000 people. I don't know the exact number. Those interested, they can check. But around these 20, between 20 to 40, 50,000 sample was taken from across the country in a very well diversified manner. And that from based on that sample. So what is the idea? Based on the sample of 20, 30,000 people, you are trying to find out, and that sample is well diversified in terms of the geography and length and breadth of the country, as well as the sample is random. Random meaning we are not deliberately picking up people. We are not deliberately picking up people who are less exposed or more exposed. We are just taking the sample at random, so that all things that are there in the population, they get included in the sample also. So based on the 20, 30, 40,000 people, we are trying to find out what is the level of presence of, say, COVID antibodies, and then we will be generalizing the results from that sample to the entire population of 140 crore people. So this is the necessity. This is the need of our. Similarly, you see in every elections, and now also elections are going on in 5 assembly states. Again, we will have national general elections in 2 years. If you take that example, again, there are a lot of opinion polls and exit polls that come. So what are they doing? There are now over a billion voters, over a billion eligible voters probably in India. So are they taking survey of each of the voters for a national general election? Obviously, it will require too much cost, time, effort. It is not possible. So again, they are taking a well-diversified sample, sufficiently large sample, diversified meaning that all sections of the population should also be included in the sample, and at a random basis. For example, if you're taking a survey of political parties, obviously you would not like to take a survey of only those people who favor a particular political party or are against a political party. That would bias your results. So you would take a well diversified and random sample from all socioeconomic groups, age groups, geographies, gender, all types of backgrounds. So that is another example of a survey. And similarly, there can be many other surveys. I am a person from management. So we also have a lot of marketing surveys, consumer surveys, all kinds of surveys are there. So the idea of inferential, what basically distinguishes inferential statistics from descriptive analysis, which you also I saw in the schedule, you covered it yesterday. by till yesterday's session. So descriptive statistics or analysis is about the analysis of the sample data. And inferential analysis is about jumping from the sample and being able to generalize the results to the entire population. This is the fundamental idea behind inferential statistics. And how this is done? This is done through what we call as the process of hypothesis testing. So the participants are from diverse backgrounds. Some of you may be already aware of hypothesis testing in your maybe statistics course or any research methodology course, but still I will not go into the complete length and breadth of hypothesis testing because we have limited time, and my primary focus would be to explain concepts and techniques and then do it in R. But I would still be giving you a fair bit of idea in my own way, so that anyone who are aware and not aware, they get a fair bit of idea about what is hypothesis testing. So when we say that we have collected this much sample and this is our result, we need to validate in a way. If I talk loosely because of my mixed background of audience, so we need to validate that result. What is the probability, for example, that our results of the sample are going to hold for the entire population? We need to obtain this. We need to find out. We cannot just implicate or generalize our results from sample to population. So we need a process, a statistically verifiable process, which is the process of hypothesis testing. So hypothesis testing is the primary key thing which we do in inferential statistics. So quickly starting with hypothesis, many of you might already be aware. So hypothesis is any statement or assumption, but there is a very clear distinction. It is a statement or assumption that can be verified, that can be proven right or wrong. So every claim, every statement is not a hypothesis. Only that which can be verified, that can be, you can come to a conclusion that yes, we can reject this or we cannot reject this. Only those statements are hypotheses. And hypotheses are of two types, null and alternate. So basically, if I give you an example, suppose I tell you that the relation between two people or two countries or two companies is bad. Just let's say that this is our hypothesis. So natural instinct would be that why are you assuming that it is bad? You should have some, and before that you would ask that what is the basis of your claim that the relationship between two countries or two companies or two individuals or any two entities is bad or even good. Even if you say it is good or friendly, for that also you would say that why are you assuming? Is there any basis? So if you understand the psychology of it, then it is much easier to remember these things rather than just rote learning that this is null, this is the way we write null, this is the way we write alternate. Much easier way is if you understand what is the psychology or rationale behind framing it like that. So we in null we frame it like that because we start with no assumption. Even if we think that there is something, we say in null that there is nothing. That is, there is no effect, there is no impact, there is no difference, there is no relationship between variables. Now, the process of hypothesis testing has been established in such a way that we tell that bring up some data, bring up some evidence to the contrary, and then if the evidence is substantial, we will reject the null hypothesis. So in null hypothesis, we say that there is no effect, no impact, no relationship, no difference. You collect the sample data, and then you bring up evidence. If the evidence is statistically strong enough, then we can say that null hypothesis can be rejected, otherwise not. And what we want, what we think is right, is put in the alternate or research hypothesis. For example, in a business context, if we think that advertisement expenditures will have an positive impact on sales, even then what we will do is that in the null, we will put that advertisement expense has no effect or no impact on sales revenue. And what we think is right from a researcher's perspective, that's why the alternate hypothesis is also called a research hypothesis. So what we feel right from a researcher's perspective or an analyst's perspective, we put it in the alternate. So in null, we will put advertisement expenditure has no impact on sales, And in the alternate or research, we will put that advertisement expenditure has an impact on sales. So the process, we don't touch the alternate. We frame null, we collect data, and we reject or not reject the null hypothesis. If we are not able to reject the null hypothesis, then there is very weak support for alternate. And if there is substantial evidence against null, then it provides support for the alternate. That's how we procedurally go for hypothesis testing. I will give you many more examples. I will give you many more examples when we go down to the specific parametric and non-parametric techniques. I will give you multiple examples about the framing of null and alternate hypotheses. Now, these null and alternate hypotheses, few basic concepts which is required. I will just cover them quickly. So these null and alternate hypotheses can be one-tailed or two-tailed. So when you are doing a directional test, for example, in very simple language again, I can say that two persons are not related with each other. Person A and person B are not related with each other. And in the alternate, I can say that both of them are related. If I say that both of them are related, but I do not say whether they are friends or foes, then it is a two-tailed test. So the null is same, that they are not related to each other. But if I say that they are related to each other, but I do not give any specific direction that whether they are positively related or negatively related, that is in case of individuals, are they friends or enemies? For example, in case of macroeconomic variables, I say in the null that interest rate does not have an impact on GDP. But in the alternate, I say that interest rate has an impact on GDP or investments or whatever. But I do not give a direction that whether interest rates have a positive impact or a negative impact. Then it is a two-tailed test. If I put a direction to it, that it is either a positive impact or a negative impact, then it becomes one-tail. For example, in this case, we can say that interest rate has a negative impact on GDP. Higher the interest rates, generally, we have lower investments and lower GDP. It has a negative impact. Or higher inflation has a negative impact on economic activities in general and demand and GDP in particular. So when we are specifically saying that it has a negative impact, then it becomes one-tailed test. Similarly, if we are saying in the earlier example, as I was saying, that advertisement does not have an impact on sales, that will be the null hypothesis. Like interest rate does not have an impact on GDP, inflation does not have an impact on economic activities. All this will be null hypothesis. No impact is null hypothesis. But the one tail or two tail is decided depending upon how we frame the alternate hypothesis. So in alternate hypothesis, if I'm simply saying that they have an impact or relationship, then it becomes two-tailed. But if I specifically say that the impact or relationship will either be positive or negative, then it becomes a one-tailed test. For example, just like we said that inflation or interest rate has a negative impact, that will become a one-tailed test. Similarly, we can say that advertisement has a positive impact on sales revenue. That will become the right tail, or the again a one tail test. So if it is on the positive side, it becomes right tail test, as you can see in the diagram also. And if it is on the negative side, it becomes a left tail test. So, but both of them will become the parts of what we call as one tail test, because you are testing only on the one side. It happens many times, in real life. For example, if the in examinations, for example, in case of students, in examinations, always there is some minimum marks that you have to score. Otherwise, you will fail. There is no upper limit. You can score as much as you want. But there is a minimum threshold, which is the passing marks that you have to pass. So a student will fail if they do not clear the minimum passing marks. So we are talking about a limit on the left side or the left tail. Similarly, in say pharmaceutical industry, when we are putting chemicals in medicinal drugs, those chemicals may have a side effect on the people who take the medicine if the quantity is too much. So we have an upper limit in those cases. If there is slightly less amount of chemical, that may be fine. But if it is more in a particular medicine capsule or something, it may be harmful for the patient. So we put an upper limit that the proportion of chemical should not be more than this in the medicinal tablet or syrup or whatever it is. So in that case, it would become the upper tail test. In some cases, it becomes a two-tail test. For example, you all have consumed, say, chips or biscuits. If I take the example of chips, so there are so many competing brands, and we all like the taste of potato, though it is quite injurious to health in the long run, especially if we overconsume. But once in a while, we always like to have. So if the companies put too much quantity in the packet, then they will be unnecessarily increasing their cost, because for them, the selling price is same 5 rupee, 10 rupee or 20 rupee packet. But if you are unnecessarily stuffing it with more chips, then you are simply increasing your cost and removing your profit margin. So you don't want to go beyond a certain level. Similarly, if you put too less of chips in one packet and you do it consistently, then customers are also very smart. And there are a lot of competitor brands. They will become fed up that, oh my God, look at this, what they are doing. How much chips, how much quantity we are getting in 5 rupee or 10 rupee packet. It's worth useless. And immediately the friend will say that, okay, why are you using this brand's chips? Use this brand. So if you put too less chips in a particular packet, and you do that repeatedly, over time, you will begin to lose customers because you are providing them too little value for their money. And if you put too much, it will be costly. Your profit margin will reduce. So companies would like to test a hypothesis that the quantity in a chips packet, this is an operations issue, production issue, that the quantity in a chips packet is neither too less nor too much. So this is an example of a two-tail test. So I can go on and on, but I think if there is something more that needs to be clarified, we will take it up in doubt session. But I think you would have understood the idea of one tail and two tail tests, because we will be carrying out the one tail and two tail test using arrows. Now, this is a very important matrix for decision making that I want you to understand. So let's take a very simple example of judiciary. So so we have a truth, we have what is called the truth. So for example, in a criminal case, if someone is charged with a crime, so the truth is that either the person has committed the crime or the person has not committed the crime. Either case, maybe one of them can be the truth version. And the decision of hypothesis testing is like the judgment that we get from judiciary. So judgment there can be that yes, the person is convicted, or no, the person is not convicted. So if the person is guilty and they are convicted, then obviously it is a correct decision. Similarly, if the person is not guilty and they are not convicted, that is also a correct decision. But we have what is called errors. So for example, what I will come to this particular slide, but in general, if we talk, we will have error in two cases in general. So for example, if a person is not guilty but has been convicted by the court for the crime, that is an error. And similarly, if the person is indeed guilty but has not been convicted by the court, so due to lack of evidence or whatever ground, they have not been convicted, so that will also be an error. But the correct decision will be if the guilty person is convicted or the innocent person is not convicted. So accordingly, if the null hypothesis is true, then it should not be rejected. But if we are rejecting it, then we are committing what we call type 1 error. And this type 1 error is also called as alpha. This, I think, you should know, because if you're doing or understanding hypothesis testing and inferential statistics, you must understand null, alternate, type 1, type 2, one tail, two tail. All these things you must understand. These are fundamental concepts. So if the null hypothesis is true, in any case, whatever is the null hypothesis, I gave you so many examples of null hypothesis. So if it is true, but we are rejecting it based on the hypothesis testing process, we are committing what we call as type 1 error. And this type 1 error is identified or denoted by alpha. Similarly, if the null hypothesis is not true, but we are not rejecting it. If the null hypothesis is not true, then ideally we should be rejecting it. But if our hypothesis testing is not able to reject it, even when it is not true, then we are committing what we call as, what we know as type 2 error, type 2 error or beta. So to understand this practically, I will have to first explain to you the concept of level of significance, and then which is our main thing. And then I think you will be able to understand that how, what are the real life uses of these type 1 and type 2 error. And you will also be able to appreciate the trade-off that exists in type 1 and type 2 error, because for statistics tests and classes, we tell students that this is the level of significance or something. But in real life, as researchers, sir is also there, ma'am is there, many faculty members would be participants. So in real life, we assume that what is the level of significance and we decide. So it's we who are setting. The only thing is that you should set the rules. You should decide the rules before the play starts. You should not see the results and bend your rules. The only fair thing is that. Anyways, so coming back, so how do we decide about, I told you that we test null hypothesis. So in a very, very plain, language, I would, if I take a pardon from statisticians. So in a very plain and basic way that I would like to explain is that what we use is the test of significance approach. I will not go, there's one more approach, which is called the confidence interval approach, that involves a lot of calculation of upper and lower limits and parameters and all that. So now when we are talking about two approaches, confidence interval approach and test of significance approach. So confidence interval approach, again, some of you who are from statistics background would be aware of this. It requires setting up a confidence interval around the sample mean. So around the sample mean, we take plus minus standard error into the t or z value, and that t or z value depends on our confidence level. So there is a lot of statistics and calculation involved. But fortunately, what has happened in the years that as statistics and these analytical techniques are being used across the discipline. For example, we would have never imagined, say 10 years ago, that a student from psychology or humanities is reading these techniques. But now as they have become interdisciplinary, and this great program is helping in that. So it is no more a foundation that you do that process also only. And the softwares also have evolved that they now provide the exact p-value or the actual level of significance, which actually bypasses the whole confidence interval thing, and you can directly make conclusions over it. So for you, the basic thing is that we can use either of the approaches. And since the test of significance approach is the most direct and now more commonly used in reporting results, and all softwares keep producing, R will also provide you. So we will be understanding the test of significance approach. So for understanding the test of significance approach, I know it is a little technical, but I will try to explain it in a very simple way. So I think most of you will be able to understand it, despite whether if you have this background or not. So just assume that what we were doing, just recall what we were doing in hypothesis testing. We framed the null hypothesis as no impact, no relationship, no difference. And in the null hypothesis, now we are looking to test the significance. We are looking to test the significance of that null hypothesis. Now, we would need basically a probability figure. You all know that probability ranges from 0 to 100%. If something has a 0% probability, that means that event will not happen at all. And if something has a 100% probability, that means the event is certain to happen. It will always happen. It will surely happen. But obviously, real life events are in between. They are neither 0 nor 100. Now, what we need is that we need a probability of null hypothesis being true. Just then this is a very, very important term, which is called the actual significance or the p-value. P-value is basically the probability value. So this p-value or probability value, I have written the technical definition here, but it basically is the probability of null hypothesis being true. So if we obtain the probability of null hypothesis being true, then we can conclude whether the null hypothesis should be rejected or should not be rejected. And remember, the thing which we wanted to prove, we have put in the alternate, but the conclusion regarding the alternate will depend on what happens with the null. So for example, now let me complete the chain for you. P-value is the significance or probability in favor of null hypothesis, or probability of null hypothesis being true in very simple terms. So if the p-value is very high, so obviously we cannot reject the null hypothesis because the probability in favor of null hypothesis is very high. And if probability in favor of null hypothesis is very high, so it means that our alternate does not have statistical support. And if p-value is very less, then the probability in favor of null hypothesis is very less. So if it is very less, then we can go on to reject it. And in that case, we will have substantial support against the null and by default in favor of the alternate. So this is the p-value approach that is most commonly followed. So no matter what is the underlying test statistic and what is the underlying test distribution, all the softwares nowadays compute and give you the p-value. And this p-value is used for interpretation in the process. Now the question, now you understand that p-value can be used to decide about the null hypothesis and then and accordingly about the alternate also. But the question is that what should be the level of this p-value? What should be the acceptable level of p-value? So you may say that it should be around 50%, 20%, 30%, 40%. But actually in real life, we commonly set the level of p-value, the benchmark level, as only 5%. And that benchmark level of p-value is called this alpha. So this alpha is the level of significance or the benchmark value of p-value that we set. So what I'm trying to say is that we set the criteria for null hypothesis as 5%. We say that a null hypothesis will be rejected only if it does not gather at least 5% probability in its favor. If a null hypothesis based on the sample data has more than 5% probability, if we are taking alpha as 5%, which is the common benchmark, then if a null hypothesis has a probability more than 5%, then we should not decline or reject it. You would ask, why 5%? Why not 50%, 40%, 30%, 20%? See, you would say that this is very unfair. You would say that what we have put is in alternate, and we can get support for alternate only when null is rejected. But to reject null, you have kept such a low criteria. Imagine having a passing marks of 5% in an examination. Almost all students will pass if the passing marks is 5%. So you would say that it is actually unfair towards the alternate hypothesis that the alpha or the benchmark level is set as just 5%. But the reason is that we have to be very, very careful. The reason is that there are two reasons. First, if you want to prove something, you have to bring substantial evidence. Normally, what we would assume that there is no relationship, no impact, no effect. Like there is no, that for example, in judiciary also, we assume that a person is innocent until proven guilty. Every person who is charged with a crime or offense is innocent until proven guilty. That's accepted worldwide norm for judiciary. So normally we will assume that null is true. Now you have to bring substantial evidence to prove that null is not true. That's the first thing. Because you are saying you want to prove something, you want to establish a relationship. Because if null is disproven, we are getting support for the alternate. And alternate says there is a relationship, there is an impact, there is a effect. So if this has to be proven for the entire population, and the second point is that we are not making conclusions about the sample. We are going to make conclusion inference about the whole population. So the first thing is that you want to prove something against the idea, against the initial or default state of nothing. You want to prove something, so you need to bring evidence. And second thing is that you want to prove that thing not just for sample, you want to be proving that thing and generalizing that result for the entire population. So we have to be very, very sure if we have to reject null, because rejecting null will mean huge support for the alternate. That's why we keep a very stringent criteria of just 5%. So 5% criteria means that there has to be 95% of probability or evidence against the null. Only when we have 95% evidence against the null, then we will reject the null hypothesis. If we do not have that much evidence against the null, we will not reject it. Or on the contrary, if null has just even 5% support, then also we will not reject the null hypothesis. So to prove something and from the sample data to be able to prove it for the entire population, you need very, very strong support. And that support will reflect in that support should reflect in a very, very small p-value. So look at this lower part of this slide. So if p-value is less than 5%, I have also given other two commonly used, less commonly used benchmarks like 1% and 10%. In some researches, you will also find that instead of 5% alpha is 5%. This alpha or 5 alpha is called the level of significance. Basically, it is the passing criteria for null hypothesis in terms of probability. If null hypothesis has this much probability, it will pass. Otherwise, it will not pass. So most commonly used, as I said, is 5%. But in some researches, we also see that 1% or 10% is also used. So if the p-value is less than 5, 1 or 10%, then what we say is that null hypothesis can be rejected because we have very little evidence. See, it is less than even 5%. Less than null hypothesis, less than 5%, meaning that in less than 5 out of 100 cases, 5% means 5 out of 100. So if the p-value of null hypothesis is less than 5%, that means that null hypothesis will not be true in more than 95 cases, or it will be true in less than 5 out of 100 cases. Because I told you this p-value is probability of null hypothesis being true. So if the probability of null hypothesis is being true is just 5 out of 100 or less than 5 out of 100, then we have substantial evidence against it. So we can say that null hypothesis can be rejected. Or we write it like that, we have enough evidence to reject HO being the null hypothesis. But less than 5% does not mean 0%. Less than 5% does not mean that the probability in favor of null hypothesis is 0%. It is still something. For example, it may be 4%. If the probability is 4%, then it means that in 4 out of 100 cases, the null hypothesis can be true. So on the safer side, we do not say that null hypothesis is false. We do not write this kind of language that HO is false, because for something to be false, its probability should be 0. But the probability is not 0, it is less than 5%. It may be 4%, 3%, 2%, 1%, but it is not exactly 0. So we do not write these things. So I have written here, you should never say like this. So you should not say, even if the p-value is less than 5%, you should not say that HO is false or the alternate is true. Why we can't say that alternate is true? Because for something to be true, it should have 100% probability. But this is not the case. If null's probability in favor of null is less than 5%, alternates indirectly you can say that alternate can be true in more than 95 out of 100 cases. but still that does not mean 100 out of 100 cases. And even if it means 100 out of 100 cases, then still remember that whatever you are concluding based on a small sample. So for example, I have taken a sample of 20,000 people. Someone else can take a sample of 20,000 people. Someone else can take a sample of 20,000 people, and they may arrive at a different conclusion. So we don't know. So even if it is 100% or 0%, then also we can't conclude surely, because we are working on sample data. We are not collecting the data of entire population. So we should not say like that. And if this p-value is greater than 5%, then we say that null hypothesis cannot be rejected, or we do not have enough evidence to reject HO. This is very, very important, the language, how we write it. But we should not say that not rejecting HO does not mean that we accept HO or HO is true, or we are rejecting alternate or alternate is false. These things are not said. The idea is that if the p-value is very high, especially less greater than the benchmarks of 5%, then there is little evidence, little support for alternate. And if it is less than 5, then we have strong support for alternate. That's the whole thing of this process. Now, recall that it all depends on the passing criteria that we have set. So we have set the passing criteria of 5%. So if the null hypothesis probability is less than 5, it can be rejected, otherwise not. But in setting the criteria as 5%, we are taking the chance of making an error, because even if a null hypothesis has a probability of say 4.9%, you will be rejecting it as if it has a 0% probability. But in real life, it can be true in 4 out of 100 cases. So that is why, students, this benchmark, this 5% that I told you is also called alpha or level of significance. That is also called as type 1 error. Why it is called type 1 error? Because you are taking this much margin of error. You are rejecting any null hypothesis which has a probability less than 5%. So even if it does not have a 0% probability, but 3% probability, but you are still rejecting it. 4% probability, you are still rejecting it. 4.99% probability, you are still rejecting it. So you are taking the chance. What you are taking chance? You are taking the chance of rejecting a null hypothesis through the decision of your hypothesis testing, even when it is true. Look at this box. If you look at the intersection, what this intersection is representing, it is rejecting HO when HO is true. So even when HO is true, you're rejecting it. That's why it is called type 1 error. And it depends on the level of significance you decide. So if you decide it as 5%, which is the general benchmark, your alpha is 5%. Similarly, if you look at beta, what is beta? Beta is type 2 error. So type 2 error is the probability of not rejecting a false null hypothesis. So alpha and beta are related in a way. And this is a very interesting dichotomy that you must understand and appreciate. If you set alpha as very high, say you set alpha as 10%. So what will happen? Any null hypothesis which has a probability p-value less than 10% will get rejected. So there is more chance that a true null hypothesis will get rejected, because you have set the passing criteria as high. If you have set a passing criteria as high, real worthy people may also get rejected. So similarly, the true null hypothesis may also get rejected because your passing criteria is high, it is 10%. So if your level of significance or alpha is high, then your type 1 error will be high, the error of rejecting a true null hypothesis. But the probability of not rejecting a false null hypothesis will fall, because obviously now you're rejecting much lesser null hypothesis. Now there is very less chance that a non-true null hypothesis will not get rejected, because in general you are rejecting more. Earlier only you were rejecting those which had probability of less than 5%. Now you are rejecting everything which has a probability of less than 10%. So you are rejecting a lot more null hypotheses. So there will be very less chance that you will be making a type 2 error, because type 2 error is not rejecting a false null hypothesis. Most likely you will be rejecting a false null hypothesis. So there is a trade-off between alpha and beta. If you set alpha as high, your type 1 error will be high, which is the probability of rejecting a true null hypothesis, but your beta or type 2 error will be less, which is the probability of not rejecting a false null hypothesis. And vice versa is also true. If you set alpha as lower, for example, instead of 5%, we set alpha as 1%. So what will happen? The type 1 error will decline, because now we are rejecting only those null hypotheses which have a p-value of less than 1%. Earlier we were rejecting for 5%, less than 5%. Now we are rejecting only for less than 1%. So there will be very less chance that you will be rejecting a true null hypothesis. Most of the null hypotheses will pass through. So your type 1 error will be less, but your type 2 error will be high, because when you are allowing more null hypotheses to pass, there may also be a null hypothesis which is actually not true, but you will allow it to pass because your criteria is very less. It is just 1%. So if type 1 error or alpha or level of significance is less, then your type 1 error is less, but your type 2 error will be high. You will be rejecting more, you will be rejecting more null hypotheses. So the probability of not rejecting a false will be, high, but the probability of rejecting a true null hypothesis will be low. So this way, alpha and beta always have a trade-off. Type 1 and type 2 error always have a trade-off. So this is it that I wanted to, distinguish. Then sample size and statistical significance. The statistical significance, which I discussed with you, is there's a complex root for those who know statistics well. There is a concept of standard error, and large sample size reduces the standard error, and hence it improves the significance of your results. But in layman's language, you can also understand. Suppose your target population is of 1 lakh, and suppose someone has taken a survey of 100 people. So how much confident you will be about those results? Very less. And suppose someone else has taken a survey of 1,000 people, then you will be much more sure. So the margin of error will be less. Similarly, if someone takes a sample of 10,000 people out of 1 lakh population, you will be much more confident about the generalizability of your results from the sample to the whole population. So larger the sample size, lower is the standard error in technical terms, and lower the standard error, it improves the value of test statistic, and again, it improves the significance. But for practical purposes, you just need to understand that larger sample size will result in greater chance of significant results. Okay, and one more term just before we wind up this part. The significance term means, we call the results significant if null can be rejected. Because what we really want to prove or what we really want to test is in the alternate, and that will gain support only when the null is rejected. So when do we call our results as statistically significant? We call our results as statistically significant when the probability value of null hypothesis is less than 5%. The usual benchmark, it can be 1 or 10% also. If this happens, we call our results as statistically significant. So we are more likely to gain significant results in large sample sizes. Also, this is also called a large sample bias, but for practical researchers, it is also fine. And one more last thing, practical advice, we have something called the central limit theorem. So central limit theorem basically says that if the sample size is large enough, your sampling distribution will have the normal shape. And if we have the normal shape, then we can, if it follows normal distribution, then we can apply all the usual tests like T, Z, F. All these tests are related to the normal distribution somehow, directly or indirectly. So generally, it is recommended that your sample size for any kind of inferential analysis should be more than 30 or 50 and preferably 100. 30, 50 is also fine, but preferably 100. So large sample size would mean that you have your data, your sample data can be assumed to follow normal distribution. And then a lot of tests that we are going to apply will be much more, they will be much more reliable in that case. And then I have also provided a lot of I think you have already done this. So a lot of different scales of measurement and what are the permissible statistics and permissible tests. You would have done the scales of measurement much earlier in your course. So these are some of the techniques. And we will start with parametric tests in the next session. And we will take up any conceptual doubt related to hypothesis testing and significance and their interpretation in the doubt sessions tomorrow. So thank you, everyone.